Hello and welcome to our presentation on Gibbs free energy and the equilibrium constant. Through this presentation, we're going to explore the concepts of Gibbs free energy and highlight important relationships and their significance. Now let's learn about Gibbs free energy and how does it predict spontaneity. Gibbs free energy is a thermodynamic property that predicts the spontaneity of a reaction. It is the energy in a system that can be used to do work at a constant temperature and pressure. It is defined as G equals H minus Ts, where H refers to enthalpy, T refers to temperature, and S is entropy. Now, what is the criteria for spontaneity and how is G involved in it? Well, a negative change in Gibbs free energy indicates a spontaneous favorable reaction. Conversely, a positive del G suggests a non-spontaneous reaction. Through this chart, we can see clearly that the value of del G, if it is less than 0, then it would be spontaneous, otherwise it will be non-spontaneous, and for 0, it should be equilibrium. Now let's learn about equilibrium constant, and how do we even quantify equilibrium at the first place? Well, the equilibrium constant is denoted by K, and it is the ratio of product to reactants at equilibrium. The higher the value of K, the greater preference for product formation. Equilibrium constant is a temperature dependent. It's a measure of the extent to which a reaction proceeds to completion at any given temperature. Let's assume a reaction such as this. Now, if this reaction is in equilibrium, we can write down the rates of forward and backward reactions using the law of mass action. And we know that in equilibrium, the rates would be equal. So we can substitute out the values and get a value for equilibrium constant K. If the reaction was in gaseous state, then instead of using concentration, we are going to use partial pressure to determine the value of K. Now let's learn how Gibbs free energy is related to equilibrium constant. Let's assume a reaction such as this. Now, the free energy change is related to the equilibrium constant by the equation shown on screen. Here, del G indicates all reactants and products are in standard states. Now, for a system in equilibrium, del G would be 0. That suggests the reaction would stand to be del G naught equals minus RT ln Q or minus RT ln Kp, as in gases, Kp equals Q. This equation allows us to calculate K from del G and vice versa. It provides a quantitative link between thermodynamic and kinetic aspects of a reaction. Now, in this chart, we can see that if del G is less than 0, the Kp would be greater than 1, suggesting that products are favored. Otherwise, reactants would be favored, and for the case where del G equals to 0, it will be an equilibrium state and neither will be favored. Now, let's see what is the temperature dependence of the equilibrium constant. The equilibrium constant changes as temperature varies, affecting the position of the equilibrium. We can learn about this relation using Van 't Hoff's equation. The equation suggests that ln K equals minus del H naught by RT plus del S naught by RT, where del S is the entropy, del H is the enthalpy, and R is the molar gas constant. For two different temperatures, we will get two different equilibrium constant, and their relation would be like this as shown on screen. Here K1 and K2 are equilibrium constant at temperature T1 and T2. For an exothermic reaction, del H would be less than 0 and the magnitude of K will decrease, and for an endothermic reaction, del H would be greater than 0 and the magnitude of K increase. For a graph drawn in log Kp versus 1 by T, the slope would be negative for endothermic reaction and the slope would be positive for exothermic reaction. Now, another relation is suggested from Le Chatelier's principle, which suggests that exothermic reaction will have an equilibrium constant that decreases with increase in temperature, and endothermic reaction will have a constant that increases. Now, let's see an application of everything that we have learned today in our very uncommon Haber-Bosch process. Now, we have a problem at our hand, and it is the reaction of ammonia production in industry in Haber-Bosch process. Now, there is a standard value of free energy given, minus 32.7 kilojoule, and a non-standard conditions are given where we have to calculate the del G and determine whether or not the reaction will proceed to the right. At first, we substitute the values of partial pressure in equation 3 to get the value of Q. Now, using the given standard free energy value, we can assume from the chart that the Kp is greater than 1. Then, using equation 4, we will determine the value of del G in the non-standard condition. And from that, we can clearly see that Q is greater than free from chart 2. That suggests the reaction will be spontaneous and will proceed to the right. Now, let's see some more applications of free energy and conclude today's presentation. Not only in the previously mentioned Haber-Bosch process, but in many other industrial process like the contact method, in biological process, literally in our body, oxygen binding in hemoglobin, in many electrochemical reactions, and even in drug binding, free energy and equilibrium constant works together to give us the results that we require to learn about the conditions and criteria for those reactions to take place. These are fundamental concepts in chemistry, biology, engineering, providing tools to predict spontaneity and understand equilibrium. This helps us to optimize the reaction for better yield, for better products, and of course, to learn more about the world and nature itself. That is today's presentation. Thank you for listening to us.